Welcome to this lecture series in group theory. Let us recall some basic things that we need for this lecture. So Lagrange's theorem says that the left cosets of any subgroup of a parent group G partition the parent group. Okay, and a consequence of this is that the cardinality of any subgroup divides the cardinality of the parent group, provided the parent group is a finite group. Okay, the set of all the left cosets of a subgroup H of a group G is denoted by this symbol, and it is read as G mod H. The index of a subgroup of H is defined as the cardinality, as the set of all the left cosets of H in G. In case G is finite, this thing is equal to that thing, and it is also written that way. We did not mention this explicitly, neither this fact nor this notation, but this is a simple consequence of Lagrange's theorem. Of course, provided G is finite, otherwise this makes no sense, right? So just make a note of this. And let us also recall this object. Fix a positive integer n or any non-zero integer n, then this is the set given by this orange thing. So basically consider all the cosets of nz which come from the integers which are relatively prime to n. Of course, this is a finite set. And under this binary operation, which sends a bar, what is a bar? A bar is this. That is the notation. So this binary operation just takes a bar, b bar to a b bar, and this is well defined. We discussed that. So this becomes a group under this binary operation. We will need this. And lastly, recall that for any element x in G, we define the subgroup. Well, the subgroup generated by x is simply by definition the smallest subgroup of G which contains x, meaning it is the intersection of all the subgroups of G which contain x. It is a fact which one can easily check that this is equal to the thing on the right side. Okay, regardless of whether G is finite or infinite, this is equal to that. Okay, these are the problems. And now let's get started with the material of this lecture. So fix a group G and x be an element in G. We define the order of x as the minimum of this set of all positive integers which satisfy this equation, right? Provided this thing is non-empty. Because if this is empty, one can't even write the minimum here. And we also write order of x is infinite if this set is empty. So in a sense, we are saying, suppose there is an integer n for which this holds, then the order of x is the minimum positive integer for which this equation holds. And if there is no n for which this equation holds, we just simply write order of x as infinite. That's it. So very simple definition, and let's see some examples. So first example is, suppose G is your group of all integers under addition, and x is 1, then the order of x is infinite, clearly. Now suppose the group is z mod nz, and x is 1 bar, meaning the coset of nz coming from 1, this thing, that is 1 bar. Yeah, so I've written it here. So what is the order of x? Order of x is n. Again, one can easily check that. Suppose, in particular, again, G is z mod nz for n equals 4. Then what is the order of 2 bar? The order of 2 bar is 2. And you can play around with other examples. Okay. So here is an interesting fact, is that suppose G is a finite group, then order of x is finite, meaning there is an integer n, non-zero integer n for which this happens. Right? So it's interesting that in a finite group, the order of any element is finite. It's interesting in the sense that it's not immediately obvious, although one would expect such a thing. So why is that? So consider the sequence x square, x cube, and so on. Just keep going. So then, since G is finite, there must be two things in this sequence, or I should say two different I and j, such that x to the I equals x to the j. Because otherwise, since all of these are ultimately members of G and G is finite, it would mean that if all of these were pairwise distinct, then G would be in fact infinite. So these cannot be pairwise distinct. Some two of these things must be equal. So what I'm trying to say is that thus there exist I and j with I not equal to j such that x to the I is x to the j, which implies x to the I minus j. Let's say j greater than I. In fact, it doesn't matter. So j greater than I, and therefore x to the j minus I is identity, right? Which implies that x has finite order. So this is one way to notationally express that x has finite order. Why? Because j minus I is a positive integer, and this equation holding means this set is non-empty. And one can then take the minimum, and that minimum is going to be some positive integer, and that's it. So that's very nice. And now another very interesting proposition. Suppose G is a group and X is an element of G, which has finite order. And let's say the order is n, so n is some positive integer. And now if k is any integer with this property, that x to the k is identity, then n divides k. All right, so let's prove this. So let k equals nq plus r, where q is some integer and r is in this range. So this is by division with remainder theorem. All right, so thus x to the k is x to the nq plus r, which one can see is actually equal to that. All right, so let's take the middleman out. But x to the k is identity, that's the hypothesis. What about x to the n? X to the n is also identity because n is the order of x. So we get that, but this means e equals x to the r. Now what we really want to show is that r equals 0. That is the only way n can divide k, and that so we want to show that r equals 0. Now if r were positive, then what we have shown is that there is some positive integer strictly smaller than n which satisfies this equation, but that contradicts the definition of order of x. Order of x is supposed to be the smallest positive integer such that if you raise x to that power, you get the identity. So if r were greater than 0, we would have a contradiction. And therefore, r equals 0 and we are done. R equals 0 immediately implies k equals nq, and that therefore n divides k. All right. And now this proposition connects the notion of order with something else, which is not obvious immediately from the definition, but okay, we need to prove this. So G be some group and X be an element of finite order. Then we want to say that order of X is same as the cardinality of the subgroup generated by X. And this piece is just a matter of notation. Instead of writing cardinality, we also use the symbol. For any group G, instead of writing cardinality of G, we may write O of G, meaning the order of G. This is just a piece of notation, nothing mathematically interesting happening here. The only mathematically interesting thing is here. So here is a proof. Let n be order of x. Since x has finite order by assumption, this is legitimate. Consider this subset of G. And first note that the cardinality of S is n. Why is that? Because if two things here were, two different indices gave the same value, so let's say perhaps we had x to the I equals x to the j for some I and j distinct, and j greater than I, let's say, so then we would get x to the j minus I equals identity. But j minus I would then be strictly less than n. And that would contradict the fact that n is the order of x, because j minus I is also a positive integer. I and j were distinct. So just convince yourself that the cardinality of S is actually n. And another important thing to note is that S is a subgroup of G. So why is that? The thing is, because x to the n equals identity, if you multiply two things and the index and the corresponding index exceeds n, then because of this you can kind of wrap around and come back. So in a particular example, suppose n were equal to 5, then S would have become this set. And suppose we multiplied x to the 3 with x to the 4, we would get x to the 7, which is x to the 5 plus 2. which is that. And since x to the 5 is identity, this is x square, which again falls inside S. So this, because of this wraparound thing, this S is closed under multiplication. And similarly, you can show that S is closed under inverses. So just convince yourself of these two things. Nothing very hard here. So thus, since the subgroup generated by X is the intersection of all the subgroups that contain X, the above working in particular shows that this subgroup generated by X is contained in S, because S is a particular subgroup that contains X. But clearly this is contained in this set. And lastly, this set is actually the subgroup generated by X, which we discussed in the recall. So because of the sandwich, we have this is equal to S, which implies cardinality of the subgroup generated by X is the cardinality of S, which implies N. Well, that's it. That's what we wanted. So that's it. All right. So that's a nice proposition. Also, I want to mention that this finiteness here is not required. This is true for any group. So if X had infinite order, we would have this is infinite and this is also infinite. So I leave that as an exercise. All right. Lastly, not lastly, but importantly, suppose we have a finite group and X is some arbitrary element. Then we have already shown this previously. This is the interesting part. So by Lagrange, we have cardinality of any subgroup, and hence this particular subgroup divides the cardinality of G. But by the previous proposition, this is same as saying order of X divides the order of G. And just to recall, order of G is nothing but the cardinality of G. Okay, so it's a one-line proof by Lagrange theorem and the previous proposition. Previous proposition showed this, and we just used that. Okay, so that's very interesting. A nice corollary of it is that if G is a finite group and X is an element of G, then X to the order of G is identity. Again, this is not obvious immediately from the definition of a group, but let's prove this. So what we have is X to the order of X is, let's say order of X is N, otherwise we get confused in the notation. So before I go ahead, let me just mention one thing. Since G is a finite group, we have shown that order of X is finite, so this is legitimate. Okay, so let's say order of X is N, and by the previous proposition, let order of G equals NQ for some integer Q. Okay, so that's immediate from the previous proposition. There is one such integer Q. So thus, since N is the order of X, we have X to the N equals E, which implies X to the NQ equals E, which implies X to the order of G equals E. And that's it. So this is a very useful fact. And now let us put it to use. Before that, before we put it to use, I need to discuss this simple note. So suppose we have a non-zero integer and we have two integers a and b. Then writing this is same as writing that. Why is that? Because recall in the previous, or maybe in the last to last lecture, I don't remember, but we discussed this fact that if H is a subgroup of G and XH is YH for some elements X and Y in the parent group, where the parent group is G, this happens if and only if Y inverse X belongs to H. If G were abelian, this thing would have been written in this fashion: X plus H equals Y plus H. If and only if minus Y plus X in H, which is the same as saying X minus Y in H. So this second one is just a notational thing. In the abelian case, we write it that way. So since Z is an abelian group, this is how we write the cosets of this particular subgroup. Again, that's not completely necessary, but we do this. And now if we apply this this particular observation, we see that the above thing is same as saying A minus B belongs to NZ, but this is same as saying N divides A minus B, which is same as saying this. Sorry. So that's it. This observation is crucial for the next thing. So this is what we are going to do. We are going to reprove Fermat's little theorem using the things that we just discussed. So fix a prime P. Then for any integer A which is relatively prime to P, we have this equation. Okay. So how do we do this? We will consider this group. Let G be this group, Z mod P Z star. And let X equals A plus PZ, which is an element of Z mod PZ star, of course. This is an element of G, because A is relatively prime to P. So we have that. And thus, X to the order of G is the identity element of G, which implies X to the P minus 1. What is order of G? Order of G is P minus 1. This is equal to the identity element of G, which is that, right? But now what is X to the P minus 1? X to the P minus 1 is A plus PZ dot A plus PZ, P minus 1 times. And the binary operation in Z mod PZ star is such that this thing is nothing but A to the P minus 1 plus PZ. Right? And therefore, by the observation we just made, this just says that this is congruent to 1 modulo P. So that's it. It's a very short proof and very clean proof of Fermat's little theorem. Just beautiful. Okay. And I leave this as an exercise to prove Euler's theorem, which is a generalization of Fermat's little theorem, and is some positive integer greater than or equal to 2. Then we have that. Basically, you just apply everything we just did to this group. The cardinality of this group is phi n, and immediately the same proof gives you Euler's theorem. All right. So as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.